Okay. All right, so this chapter is organic compounds, cycloalkanes, and their stereochemistry. And I'm at home, so I should be able to do everything on TL draw. We'll see if that's gonna work out how I want it to. I might just do it on paper. But I already did most of this chapter, I think, or maybe not most, but I did a good amount of this chapter. All right. We'll see numerous instances in future chapters where the chemistry of a given functional group is affected by being in a ring rather than an open chain. Because cyclic molecules are encountered in most pharmaceuticals and in all classes of biomolecules, including proteins, lipids, carbohydrates, and nucleic acids, it's important to understand the behavior of cyclic structures. Although we've only discussed open chain compounds up till now, most organic compounds contain rings of carbon atoms. Chrysanthemic acid, for instance, whose esters occur naturally as the active insecticidal constituents of chrysanthemum flowers, contains a 3-membered cyclopropane ring. Should we try to name this? I love the naming stuff. Nomenclature is like my favorite right now. I think that. All right, let's try to name this. So we have a 4 here. So the 4 is or wait, this isn't actually 4. This is a 3. 1, 2, 3, because this is the 4th here. So if there's a tie, that means that we have this is the main group. So then I don't know what the ordering is. I guess the ordering is to make it the numbers are minimal. But then, okay, hold on. Find the parent, name the substituents. And then if there's a tie, you try to make them minimal. So in this case, this compound would be 1, 2, 3. We haven't learned how to name any of the double bond stuff, but I'm going to guess it's going to be like 1-ene, 2-methyl propane, and that's going to be on the, this is going to be, this could be the first group, maybe, because this is going to be 1,1-dimethyl cyclopropane. This, oic acid. Wait, how do you do that? Oh, that's weird, because we have a carboxylic acid here. I don't know how you do it when it's in the middle. All right, let's look up chrysanthemic acid and see what the IUPAC is. Bro, I should revive chemical of the day. Okay, yeah, so they have the 2,2, so 2,2-dimethyl, 3, 2-methyl, enyl. You do enyl for the double bond. You don't do ene, you do enyl. Oh, that makes sense, actually. So 2-methyl, but why is it prop? Why isn't it propyl? That's kind of interesting. I guess you only have one il in the whole thing. So it's 2,2-dimethyl, 3, and then because M is, but wait, where's the 1? Here's the 1. But I wonder why 1 goes at the end. Yeah, why does the 1 go at the end? What is our formula again? If we go back up to, let's duplicate this for, it's always good to have 3, I think. So if we go back up to naming cycloalkanes, or not cycloalkanes, we need to go back to naming alkanes. Suffix, what is the primary? So we really haven't done any of this yet. We've only really done locants and prefixes. But so that's what so did they do oic acid, or they just said carboxylic acid? They just said carboxylic acid. But then why? Then it's at the end? Bro, that's crazy. So, okay, but it's not so bad. The only thing is, the weird thing is that you what do they call it? Suffix? Is it called suffix? The suffix is interesting. All right, let's keep going. All right, so we kind of got this. Yeah, it was like 1-enol, or it was, what was it? 2,2-dimethyl, 1-enol, 2-methyl, or no, but it went 2-methyl prop, 1-enol. All right, that's easy. All right, prostaglandins, potent hormones that control an extraordinary variety of physiological functions in humans, contain a 5-membered cyclopentane ring. Steroids such as cortisone contain 4 rings joined together, 3 6-membered cyclohexane and 1 5-membered cyclopentane. We'll discuss steroids and their properties in more detail in chapter 26 or 27. Is that just an alcohol group, or is there another name for that that's more specific? It's definitely not carboxylic acid, though, because but it's like an ether. It's kind of like an ether thing going on here. Okay, naming cycloalkanes. Saturated cyclic hydrocarbons are called cycloalkanes. Because cycloalkanes consist of rings of CH2 units, they have the general formula CH2N or CnH2n and can be represented by polygons in skeletal drawings. Substituted cycloalkanes are named by rule similar to what we saw in section 3.4 for open chain alkanes. For most compounds, there are only 2 steps. Step 1, find the parent. Count the number of atoms in the ring and the number in the largest substituent. If the number of carbon atoms in the ring is equal to or greater than the number in the substituent, the compound is named as an alkyl substituted cycloalkane. If the number of carbon atoms in the largest substituent is greater than the number in the ring, the compound is named as a cycloalkyl substituted alkane. Okay, you got to get used to this alkyl stuff. It describes like what's the parent and what's not the parent, basically, I think. So in this case, 5 is greater than 1, but in this case, 4 is greater than 3. So 1 cyclobutyl or cyclopropylbutane. Step 2, number the substituents and write the name. For an alkyl or halo substituted cycloalkane, choose a point of attachment as carbon 1 and number the substituents on the ring so that the second substituent has as low a number as possible. If ambiguity still exists, number so that the third or fourth substituent has as low a number as possible until a point of difference is found. So 1, 2, 3, 4, 5, 6, 1, 3 dimethyl cyclohexane, not 1, 5 dimethyl cyclohexane. Okay. Though the interesting thing happens when you have something happens when you have like a 113 or 331. It's like 331 is not as good as 113. That wasn't obvious to me. Okay. 2-ethyl. Did it say the naming thing with the alphabetical thing? Not yet. When 2 or more different alkyl groups, when 2 or more different alkyl groups are present that could potentially take the same number them by alphabetical priority, ignoring numerical prefixes such as di and tri. But not iso. iso counts. So 1-ethyl, 2-methyl cyclopentane, E before M. But here it'd be 2-ethyl, 1-methyl cyclopentane. If halogens are present, treat them like normal alkyl group or just alkyl groups. So what are they saying? 1-bromo, 2-methyl. Okay. 1, 3, 5. So 1-bromo, 3-ethyl, 5-methyl. But you wouldn't do 1-bromo, 3-methyl, 5-ethyl because you are trying to alphabetize it. No, this one's interesting. 1-methyl propyl cyclobutane or sec-butyl cyclobutane. The second, what is it? Sec and, is it tri? Tersh, tert. Sec, tert, and quat. Actually, is quat anything? Quat isn't a thing, I think. I forget if quat's a thing. Okay, 1-chloral, 2-methyl, 3-ethyl. So in this case, if you wrapped around, you still wouldn't get it. So you can't change this one. Okay, so I actually did all of those, so I'm not going to go through them. In many respects, the chemistry of cycloalkanes is like that of open chain alkanes. Both are nonpolar and fairly inert. There are, however, some important differences. One difference is that cycloalkanes are less flexible than open chain alkanes. In contrast with the relatively free rotation around single bonds in open chain alkanes, there's much less freedom in cycloalkanes. Cyclopropane, for example, must be in a rigid planar molecule because 3 points define a plane. No bond rotation can take place around a cyclopropane carbon without breaking open the ring. Larger cycloalkanes have increased rotational freedom. And very large rings, C25 and above, are so floppy that they're nearly indistinguishable from open chain alkanes. The common ring sizes C3 to C7, however, are severely restricted in their molecular motions. Because of their cyclic structure, cycloalkanes have 2 faces when viewed edge on, a top face and a bottom face. As a result, isomerism is possible in substituted cycloalkanes. For example, there are 2 different 1,2-dimethyl cyclopropane isomers, one with the 2 methyl groups on the same face of the ring, and one with the methyl groups on opposite faces. Both isomers are stable compounds and neither can be converted into the other without breaking and reforming chemical bonds. Unlike constitutional isomers, butane and isobutane, which have their atoms connected in a different order, the 2,1,2-dimethyl cyclopropanes have the same order of connections but differ in the spatial orientation of the atoms. Such compounds with atoms connected in the same order but differing in 3-dimensional orientation are called stereochemical isomers or stereoisomers. The cool thing about stereoisomers, you should go through and look at, number every atom, then draw the molecular graph of the thing, and you'll see that stereoisomers are not basically the edge lists are the same. That's just another way of saying that. As we saw in section 3.6, this term stereochemistry is used generally to refer to the 3-dimensional aspects of structure and reactivity. So yeah, this is a good example. The 1,2-dimethylcyclopropanes are members of a subclass of stereoisomers called cis-trans isomers. The prefixes cis means on the same side, and trans means across in Latin, are used to distinguish between them. Cis-trans isomerism is a common occurrence in substituted cycloalkanes and in many cyclic biological molecules. Okay. So this one, I mean, these things are really easy to figure out. Trans, cis. It's like pretty obvious. Okay, I did all of those already, so I encourage you. You should go through. All right. Let's see. Did I read this? So this is kind of where I'm at now. Ring strain. Chemists in the late 1800s knew that cyclic molecules existed, but the limitations on ring size were unclear. Although numerous compounds containing 5-membered and 6-membered rings were known, smaller and larger ring sizes had not been prepared. Hold on. Smaller and larger ring sizes had not been prepared despite many attempts. A theoretical interpretation of this observation was proposed in 1885 by Adolf von Baeyer, who suggested that small and large rings might be unstable due to angle strain. The strain induced in a molecule when bond angles are forced to deviate from the ideal 109-degree tetrahedral value. Bayer based his suggestion on the simple geometric notion that a 3-membered ring, cyclopropane, would be an equilateral triangle with bond angles of 60 degrees rather than 190, and a 4-membered ring, cyclobutane, should be a square with bond angles of 90 degrees. The 5-membered ring should be a regular pentagon of 108. Continuing this argument, large rings should be strained by having bond angles that are much greater than 109. What are the facts? To measure the amount of strain in a compound, we have to measure the total energy of the compound and then subtract the energy of a strain-free reference compound. The difference between two values should represent the amount of extra energy in the molecule due to strain. The simple experimental way to do this for a cycloalkane is to measure its heat of combustion, the amount of heat released when the compound burns completely with oxygen. The more energy strain the more energy is released by combustion. Oh, yeah. So you use a strain-free acyclic alkane. Okay. Why is 6 and 14 0? I'm gonna move back over. I think this is gonna work. It's more comfortable over here. Okay. Test. All right. That's not the best. Let's see if I can do something. Okay, nice. This is good. Let me just get my notebook. Okay, the data in figure 4.4 shows that Bayer's theory is only partially correct. Cyclopropane and cyclobutane are indeed strained just as predicted, but cyclopentane is more strained than predicted, and cyclohexane is strain-free. Cycloalkanes of intermediate size have only modest strain, and rings of 14 or more are strain-free. Interesting. Or more. Bayer's theory is wrong for the simple reason that he assumed all cycloalkanes to be flat. In fact, as we'll see in the next section, most cycloalkanes are not flat. Instead, they adopt puckered three-dimensional conformations that allow bond angles to be nearly tetrahedral. As a result, angle strain occurs only in 3 and 4 membered rings, which have little flexibility. Yeah, if we look at cyclobutane, does it actually have an angle? I love this. It's just a square. That's fun, man. I like that. Um, so yeah, it does have this angle. It's not flat. For most ring sizes, particularly the medium ring cycloalkanes, torsional strain caused by HH eclipsing interactions at adjacent carbons, and the steric strain caused by the repulsion between non-bonded atoms that approach too closely are the most important factors. Thus, three kinds of strain contribute to the overall energy of a cycloalkane. Angle strain, torsional strain, and steric strain. All right, let's do it. I haven't done these problems. Each HH eclipsing interaction in ethane costs about 4 kilojoules per mole. How many such interactions are present in cyclopropane? Let's see if I can do this. Okay, so this is cyclopropane. And it has to be eclipsed, it looks like. So there's going to be 1, 2, 3, 4, 5, 6. I'm going to guess 6. So problem 4, 8. 6 HH eclipses. So then we're going to have 6 times 24, or 6 times 4 kilojoules per mole equal to 24 kilojoules per mole. So the fraction would just be 24 over 115, which whatever that is. Okay, that's going to be my guess for that. Cis 1,2-dimethyl cyclopropane has more strain 1,2-dimethyl cyclopropane. So hold on. I'm going to draw this triangle like this. And then we're going to get CH3H. So this is a wedge. This is a wedge going up. And this is CH3. And this is H. So this is 1, 2, cis 1, 2 dimethyl cycloprop. Okay. And it says it has more strain than the trans. How can you account for this? I would guess that it's because of the steric strain to nearby methyl groups. Which of the two compounds is more stable? So trans is more stable. Okay, let's check the answer. I love that this book has every answer. 6 interactions. Let's see if 24 over... Oops. Okay, yeah, it's 21%. The cis isomer is less stable because nearly eclipse each other. Yeah, I said... Okay. 4. Conformations of cycloalkanes. Oh, that's an interesting drawing. These Newman projections are weird. Cyclopropane is the most strained of all rings, primarily due to the angle strain caused by its 60-degree CCC bond. In addition, cyclopropane has considerable torsional strain because CH bonds on neighboring atoms are eclipsed. Let's try to draw the... Okay, so let's look at the... it's a Newman projection of cycloprop. So we're going to have a dot, and the dot is the one in front, and the circle is the one in the back. And so the dot is going to get an H. So we're looking down at like this. And it's really kind of, yeah. Then an H. And the circle is going to get an H. But then we're going to also have... Oh, interesting. I see how they do this. They kind of do it slightly offset And then they're going to have a line to the circle for a C, and then a line to the dot for the part of the C. And then it's just the H's. All right, that's cool. How can the hybrid orbital model of bonding account for the large distortion of bond angles from the normal 109 to the 60? The answer is that cyclopropane has bent bonds. In an unstrained alkane, maximum bonding is achieved when two atoms have their overlapping orbitals pointing directly toward each other. Oh. In cyclopropane, though, the orbitals can't point directly toward each other. Instead, they overlap at a slight angle. Ah, that's cool. The result is that cyclopropane bonds are weaker and more reactive than typical alkane bonds. All right, cyclobutane. Cyclobutane has less angle strain than cyclopropane, but has more torsional strain because of its larger number of ring hydrogens. All right, so since we're doing this, I might as well use my kit. I just bought this thing. It's kind of fun, right? It's kind of fun. The one thing that's not exactly clear is like they should be able to, because see they're all planar, but in real life they're not planar. But I don't think you can. Are they planar? Actually, there we go. That's kind of right. So we should have. Oh wow, look at this Newman projection. That is insane. Bro, Newman projection is like, that's something else, man. That's crazy. I can't. I would not be able to draw that without having a model in front of me. Cyclobutane has okay. It's not quite as flat, but it is slightly bent so that one carbon atom lies about 25 degrees above the plane of the other three. The effect. Oh, only one carbon? Wait, really? No, but no, that's not right. I guess that is right. Yeah, because you can always draw a plane between any three. And so then one of them, so if we draw the plane, let's see if I'll be able to do this. Like this. No, but that doesn't look. But no, but it's true, yeah. So for any three of them. Okay. The effect of this slight bend is to increase angle strain, but to decrease torsional strain until a minimum energy balance between the two opposing effects is achieved. Cyclopentane was predicted by Bayer to be nearly strain-free, but it actually has a total strain energy of 26 kilojoules per mole. Although planar cyclopentane has practically no angle strain, it has a large torsional strain. Cyclopentane therefore twists to adopt a puckered non-planar conformation that strikes a balance between increased angle strain and decreased torsional strain. Four of the cyclopentane atoms are in approximately the same plane, with the fifth atom being bent out of plane. Most of the hydrogens are nearly staggered. So, okay, if we can't draw this, we should be able to look at it, though. Yeah, not quite eclipsed. I think the best thing, though, is to just use the real thing. Yeah, these are pretty eclipsed. These don't look so eclipsed, though. Why don't they? Or wait, eclipsed or staggered? They don't. They don't look staggered. Yeah, you can only if you're looking at then these perspectives will not be right. So it's only projected along two carbons. So like the rest of this is kind of not very relevant. How many HH eclipsing interactions would be present if cyclopentane were planar? Oh, that's interesting. How much torsional strain would planar cyclopentane have? Ten, right? How much torsional strain would planar cyclopentane? So that's 40. Since the total measured. Oh, interesting. So 14 kilojoules per mole reduction. Interesting. Two conformations of cis 1,3-dichloro or dimethylcyclobutane are shown. What is the difference between them, and what do you think to be more stable? Let me get my kit out. This thing actually turned out to be relatively useful. It's nice to be able to look at them in front of you. All right, so I'm just gonna build some methyl. just to have. I mean, it's kind of a waste of time, but it's also fun. Okay, so there's second methyl. Now we just need to, so this is bute. So we should just be able to do this. Okay, so now we have bute. And then what we're gonna do, and this is, see, this is this thing of like, you know, one of these should have like a weird angle to it. Yeah, I think that's right. So now we just need to, it's a 1, 3. Okay. All right, so here's 1, 3, cis 1, 3 dimethylcyclobutane. But then the question is, you know, we're gonna have this increased steric effect most likely. I would kind of imagine though that this doesn't have any effect at all. Like it should be the same. But it's clearly not. This was way closer. Here, let's do this. Okay. Okay, so here's a molecule that, so this should be like, actually I wonder what this is called. But it's clear the ones that are pointing down are closer together, I think. Are they? I don't know. I think that they're the same. I think they should be equally stable. It's got to be because that I'm looking at it from a planar way, and it's not. So 10 was right. But why? Wait, how is this cis? This definitely does not look like... Oh, because it's not. This is trans. Oh, but they don't give you the 3D model for it? That's too bad. Okay, but if we were to look at this, it definitely is the fact that they're not equal. Like the angle between, if you draw this HCC angle versus this CCC angle, or actually if you draw this CCC angle and this CCC angle, they're different. Okay. All right, conformations of cyclohexane. Substituted cyclohexanes are the most common cycloalkanes and occur widely in nature. A large number of compounds, including steroids and many pharmaceutical agents, have cyclohexane rings. The flavoring agent menthol, for instance, has 3 substituents and a 6-membered ring. All right, so we have this alcohol. That's why it's called menthol. Then we have this. You could probably call this like 1-methyl ethane or something. 1-methyl ethane. I forget. Do you say 1-methyl ethyl or do you say... Let's look this up. Five methyl two. So wait, 1, 2, 3, 4. No, 1, 2, 3, 4, 5. 1 all, yeah. So 1 all, 2, 3, 4, 5. So 2 propane, 2 ill. Oh, that's how they do it. Yeah. See, this is kind of different from what the book says, where instead of like numbering the branch from the branch point, you instead just name the substance and then add the branch point in, which I prefer. I prefer this way more. 2 propane, 2 ill. That's fun. I love this new nomenclature stuff. And then cyclohexane, 1 all. Okay, good. So what was I confused about? Oh, it just had to name the group, but they didn't actually do the thing. They just did it the other way. Cyclohexane adopts a strain-free 3-dimensional shape, which is called a chair conformation. because of its similarity to a. Let's go. Let's go to cyclohexane. I don't get how it looks like a chair. Why does it look like a chair? Can I do other stuff with this thing? Fuck. Okay, so I can get this one. Now I want to rotate it. Keep getting that, but is there... There's this. It looks like a chair? How the fuck does this thing look like a chair? I mean, I... Okay, whatever. Okay, I just had cyclohexane. Let's do it again. Okay, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Okay. So this is cyclohexane. They're definitely staggered. That's for sure. Looking down any of the CC bonds, they're super staggered. That's pretty cool, actually. Another trait of the chair conformation is that there are two kinds of positions. One axial and one equatorial. Wait, what? Okay, so on this side there's okay, three. Oh, on each side there's three axial and three equatorial. What? Why are there so many drawn? Because chair cyclohexane has two kinds of positions, axial and equatorial, we might expect to find two isomeric forms. What? What?
Hey everybody, it's Professor Davis here from ChemSurvival.com and the YouTube channel ChemSurvival. I don't like them. I don't think they're good for around the perimeter of the ring in white. So we have red above and below, and we have white around the perimeter. But I can do something called a ring flip to this model. And all I have to do to effect a ring flip is to take my ottoman and make it my footrest. Take my footrest and make it my ottoman. Let's watch what happens when I do that. You ready? Here we go. Ring flipped. Now that the ring flip's complete, check that out. All the white substituents are now in the axial position, and all the red are now in the equatorial. So this process of ring flipping doesn't break any bonds, so it's just a conformational change. But it results in a wholesale interconversion between axial and equatorial. All my axial atoms become equatorial, all my equatorial atoms become axial. And I can do this back and forth as many times as I like. I can ring flip back again, now I have my red in my axial. I can ring flip again. Now my white are back in the axial position.
What the fuck? Draw a chair cyclohexane. Draw two different chair conformations of cyclohexanol showing all hydrogen atoms. I'm just gonna look at the answer. What the fuck? Oh, just like that? Equatorial, axial, equatorial. So okay, so 14. Red is E, blue E, green A. Let's see, was that right? I'm very hungry. Oh, that's freaky, man. That's weird to think about. Like, where does this go? I know it. No, I think the down goes down. I don't think there's any way. And the up goes up. Let's see. No, this one's up and this is going down. All right. Conformations of monosubstituted cyclohexanes. Even though cyclohexane rings flip rapidly between chair conformations at room temperature, the two conformations of a monosubstituted cyclohexane aren't equally stable. In methyl cyclohexane, for instance, the equatorial conformation is more stable than the axial by about 8 kilojoules a mole. The same is true of other monosubstituted cyclohexanes. A substituent is almost always more stable in an equatorial than an axial position. I mean, that kind of makes sense. Yeah, you might recall from your Gen Chem that it's possible to calculate the percentages of two isomers at equilibrium using the delta E is equal to minus RT ln K, where delta E is the energy difference between isomers, R is the gas constant, T is the Kelvin temperature, and K is the equilibrium constant. Nice. Fucking every time, bro. It's just so. Of course, more. Okay, there we go. Unitless. This is so we need to. Oh, interesting. Okay. So yeah, so 4.6. But how do you know which one is which? The lower energy one, I guess, is always going to be the one with the more. So we did reproduce this number. The energy difference between axial and equatorial conformations is due to steric strain caused by 1,3 diaxial interactions. The axial methyl group on C1 is too close to the... What are we looking at here? Yeah, okay, that's fine. That just makes sense. So probably if you look up oh, what the... Oops. What's going on here? Okay, that was weird. If we look up methyl cyclohexane, I just wonder if it's going to be in the equatorial or the... Yeah, so it's showing it equatorial. But, you know, it could be axial. Yeah, so this is going to fold down. So this would go to be up and down. All right, that sounds good to me. We're almost done with the chapter, I think. The 1,3 diaxial steric strain in substituted methyl cyclohexane is already familiar. We saw it previously as steric strain between methyl groups in Gauche Gauche butane, I think it was. I think it was Gauche butane. Gauche butane is less stable than anti-butane because of steric interference between hydrogen atoms on the two methyl groups. Comparing a 4-carbon fragment of axial the origin of 1,3 Why did I say 3 carbons away? That's... Isn't it 2? The exact amount of 1,3-diaxial steric strain in a given substituted cyclohexane depends on the nature and size of the substituent. Not surprisingly, the amount of steric strain increases through the series. Okay. Note that the values given in table 4.1 refer to 1,3-diaxial interactions of the substituent with a single hydrogen atoms, so the doubled to amount. Okay. So fluorine is pretty low. Fluorine's pretty small. Chlorine, uh, hydroxide, methyl, ethyl. What is this? Propyl. I guess this is propyl. This is isobute. What do they call it? Sec bute. No. Tert bute. Wait, do they call it tert bute? I think it's tert bute. I need to go back to that section because that thing about tert and whatever makes no sense to me. Oh, I did this earlier. Okay. Okay. All right. What's the energy difference between the axial and equatorial conformations of cyclohexanol? Isn't that just going to be 2.1 times 2? I think it's going to be 415 is going to be 4.2. Okay, and then 416. Why do you suppose an axial cyano substituent causes practically no 1,3-diaxial steric strain? That's a good question. So that would be called cyanocyclohexane. I think they call them nitrile, but so this is in the axial configuration. But you would expect equatorial would be. I have no idea because if you look at this is going to have pi bond. Well, what really is steric strain? I mean, the intuitive thing is that all the electron density. Oh, well, you know what it probably has to do with? I'd be curious if we could figure out the diaxial strain of the substituent that's CH2OH. But the thing is, then you're going to have two. What if you did CHO2? So you had like C. No, but that's directly. That's not what I wanted. I wanted like a. So let's say axial carbon, and then it's double bonded to an oxygen. So we have sp3, so this would need to be planar. So then maybe like the hydrogen goes like this. What is that called? It's like an aldehyde. Yeah, it's an aldehyde. Carbaldehyde. Cyclohexane carbaldehyde. This probably has actually a lot of steric strain. But why would it point it that way? That's what I don't understand. Why wouldn't it point it? I should probably rotate, right? I mean, this is just a sigma bond, so presumably this can be free to rotate. And then if you look down it, I have no idea what the answer is. Let's just look at point straight up. Oh, because the bond angle of a triple bond is. That's not the most satisfying answer. This one was 4.2. That's good. Look back at figure 413 and estimate the percentages of axial and equatorial conformations present. Oh, that's just using the. All right. Present figure 413. And estimate the percent. Oh, this is easy. Bromocyclohexane. So bromocyclohexane, we're going to have two. So it should be a delta E of 2. So then you go to 2 here. 1, 2. You're like 70%. Nice. All right, this chapter wasn't so bad. Getting into this type of chemistry, it's way, way different. It's like a whole new thing. Monosubstituted cyclohexanes are always more stable with their substituent and equatorial. But the situation with disubstituted cyclohexanes is more complex because the steric effects of both substituents must be taken into account. All steric interactions for both possible chair conformations must be analyzed before deciding which conformation is favored. Let's look at 1,2-dimethylcyclohexane as an example. There are two isomers, cis and trans, which must be considered separately. In the cis isomer, both methyl groups are on the same face of the ring, and the compound can exist in either of the two chair conformations. Yes, you have 4 cases now to check. Oh, wait, but this is weird. 1, 2. Oh. Okay, I was thinking 1, 3. So obviously, oh, okay, this is crazy. All right, so let's look at 1,2-dimethylcyclohexane. I think the problem is though that I don't think that we get the form that we want, right? Like this. Hold on, what are we looking at here? This is equatorial and this is equatorial. So here we have 2 equatorial, but in the case shown here we have an equatorial and an axial. Okay, but I get it. So 2 they call it diaxial. I thought they called it eclipsed. 2 eclipsed interactions. And 1 gauche. What's the difference here? This is the same exact drawing, right? I don't get what's going on here. Oh, because this flips up and this goes, but it's the same. But it wouldn't be the same if it was if it wasn't dimethyl. The fact that the 2 substituents are equal gives you like a little bit of symmetry there. Okay, both chair conformations of cis 1,2-dimethylcyclohexane have 1 axial methyl group. Both chair conformations of cis 1,2-dimethylcyclohexane have 1 axial and 1 equatorial. But why couldn't you have... Oh, because that would be trans. Right. That'd be trans. You can't do that. The top conformation has an axial at C2 and an equatorial at C3, which has 1... Wait, C2, which has 1... Oh, this is the name of that. That's so confusing. But yeah, 1,3 diaxial interactions with C4 and C6. In addition, both conformations have a gauche butane interaction. The 2 conformations are equal in energy with a total steric strain of... Okay, now the trans. In trans 1,2-dimethylcyclohexane, the 2 methyl groups are on opposite sides of the ring. Okay, my guess is that... oh, this is kind of the punchline. Is that in this case, the axial isomer is actually way better. That's what I'm going to guess, but let's read it. The situation here is quite different from that of the cis isomer. The top conformation has both methyl groups equatorial, with only a gauche butane interaction between them. Oh, actually, it might actually balance out a lot because of the diaxial interactions. The ring flipped conformation, however, has both methyl groups axial. The axial methyl groups interacts with the hydrogen. So you're gonna get 4 total of them. Yeah. Oh wow. So it's actually way worth it. Oh, that's interesting. It's kind of surprising how much energy it takes to have those eclipsed methyl hydrogen interactions. But so if you 3.8, right? So we need to delta energy diffract. This is going to be just this. So d to frac of. Oh, but you know what we want to do? We want to make this probably. It's always going to be kilojoules per mole. So do I have to do times? Let's do that. So that's 1% of the time it's actually going to be axial. So there was a double punchline. They led you to believe, hey, hold on, this time axial is going to be better. Not even close. Only 1% of the time is it going to be in this configuration. The same kind of conformational analysis just carried out for cis and trans one, whatever, can be done for any substituted cyclohexane, such as cis 1. Whoa. Okay, wait, hold on. Let's look at this. Cis 1 tert 4 bute. So this is going to be across the pond. So if you do. So here we're going to have tert butyl. I'm pretty sure tert butyl is CCH3 3. Can we actually go back to that section? Because that section is so confusing. Is it this? No, it's not that. Attached to the branching carbon atom. I don't really like the tert stuff. That one doesn't really click with me. But okay, tert butyl 4 chloro, and it's cis. So if we do this cyclohexane thing, we're gonna have, let's make this 1, 2, 3, 4. So this is gonna have, let's just do the axial drawing. So this is gonna be CCH3 3. This one, if they're axial and they're trans, then this one's pointing straight down. because this one goes down, then this one goes up, then that one goes down. Okay, so this is going to be just chlorine. Okay, so it's chlorine. I have an H here, and we have an H here. Gauche. I'm getting really hungry. Let's see, 2 hours on chemistry. That's actually pretty good. I'll switch over to physics after in like 10 minutes. So, or maybe I'll do a tiny bit of biology. Okay, so what are we trying to figure out? We're trying to figure out the strains of all this stuff. Okay, so in this case, we're gonna have. Well, I don't know what is the Cl. We need to figure that out. The Cl is so ClH diaxial is 1 kilojoule per mole. Then the methane or the methyl is 3.8 methyl H. So then where are we at here? So we're gonna have 2 times 1 plus 2 times 3.8. But is there other effects? Like what about this really should be kind of pointed up like this. Nine 9.6 kilojoules per, but I think like what about the extra like hydrogen does hydrogen not have a diaxial? I guess it's 0. Let's keep reading. As you might imagine, though, the situation becomes more complicated as the number of substituents increases. For instance, compare glucose with mannose, a carbohydrate present in seaweed. Which do you think is more strained? In glucose, all substituents on the six-membered ring are equatorial. Mm. A summary of the various axial and equatorial relationships among substituent groups and the possible cis-trans distribution substitution patterns for distributed, or no, di-substituted, geez. For di-substituted cycle is given here. Oh, because I used the wrong one. I said it was methyl, but it was butyl. This is actually 11 point. This one is actually 2 times 11.4. So we're gonna get 22.8 plus 2 to 24.8. Is that right? Oh, yeah. Why am I adding them? That makes no sense. Wait, wait, what was the problem? Oh, wait. I drew the I drew the trans form. I didn't draw the cis form. Hold on. So if this is pointing up and this is CCH3 3, and this is like this and this is CL. Okay, so yeah, so we have the okay. So 2 times 11.4 is, yeah, 22.8. So that's for the case where, yeah, let's enumerate that. So okay, so if, okay, let's say we have A and B are the subs of the, whatever dye substituted thing. So either if we have a 1-2 configuration, then A can be, and it's cis. If we're doing cis 1-2, so first I'll just write, okay, cis. So for things to be cis, then you have, if it's a 1-2 cis, then your options are A can be axial, but B cannot be axial now. So B has to be equatorial for it to stay cis. Otherwise, you can do B is axial. So if B was axial, then A is equatorial. Now I think that it alternates. If you do 1-3 configuration, now you can have them both be axial. So it's an AA or an EE. And then I think it just alternates like that. So 1-4 would be, AE or EA. And I think that that's what this table says. So if you have 1-2, you can either do this, or you can do, 1-2 trans. Oh, okay, right. And then if you do trans, then 1-2 is, AA or EE. Okay, all right, that makes sense. 1, 2, 3, 4, 5, 6. But this pattern probably goes away pretty. I mean, it's the interesting thing is basically you think, okay, this is so niche, who cares? But then you realize cyclohexane is everywhere. but the pattern does not continue for larger cyclic molecules. Like the radius is going to get big enough that this whole calculation is, except for like maybe like prox, like neighbor, what do they call it, vicinal group, like Gauss things. Oh, this stuff is not going to matter as the size of like the thing gets bigger. But the thing is, it's worth studying cyclohexane in such detail because it's everywhere. So you kind of have to just be like, all right, well, this isn't that general, but because it's everywhere, it's still important. All right. These conformations aren't of equal energy because an axial tert butyl substituent and an axial chloro substituent produce different amounts of steric strain. Yeah, the table shows the amount. Okay, yeah, that's just walking through it. Ooh, polycyclic. All right, that'll be the last section. I'm probably just going to read it. All right, let's do 418 though. Draw the more stable chair conformation of the following molecules and estimate the amount of strain in each. All right, trans. Okay, so it's a 3. So if you have a 1 and a 3, this could either be so for 1, 3, this is either going to be an AE or an EA, right? So those are the two options. So if methyl is, okay, so methyl this clearly needs to be that methyl. So if this is, so this is 1 and this is 3. So the more stable is going to be chloro is axial. And and methane, methyl is equatorial, is more stable since, and that's the thing about chemistry too, is like, is this true? Can you do this just like little algebra and like, I don't know. It seems like it should be more complicated than this. Just adding up these things, I don't know. Since the Cl to H diaxial is less than the CH3 H diaxial, the more stable is with CH3 equatorial. All right, cool. All right, now cis 1 ethyl, so cis 1 ethyl 2 methyl. All right, so if it's cis with a 1, 2, cis 1, 2, it can either be AE or EA again. All right, so let's draw structure. Jeez, that was the worst ring ever. So, so we have a 1, 2. Okay, so presumably the methyl needs to be equatorial. Or sorry, presumably the ethyl needs to be equatorial because ethyl is 4 and methyl is 3.8. So we're going to want, and then gauche is symmetric, right? So it doesn't actually matter what the gauche is, right? Because I'm pretty sure that if you have, let's just, for instance, make methyl axial and then ethyl equatorial. then you're still going to get a gauche configuration. It's kind of wild that PubChem doesn't have 3D models for, what do they call this? What is the name? Stereoisomers. You would think that they would have 3D models for stereoisomers. It's like, bro, we're living in 2026. Get it together. Okay, so I would say that this is going to have one gauche between ethyl, methyl, and then it's going to have, two CH3H diaxials. And then, oh, do I have to calculate the difference too? I think I need the difference. Estimate the amount of strain in each. Okay, so the strain here is going to be 2, for A, is going to be 2 kilojoule per mole versus here it's going to be 2 times 3.8, which is equal to 7.6. So the delta is going to be equal to 5.6 kilojoule per mole. And then in this case, we're going to get whatever the gauche is. I'll just let G be this because it's going to cancel out in the delta anyways. But so it's going to be 2 times 3.8 versus 2 times 4. Was that what it is? 4. So the difference is actually just going to be 0.4. So really, they probably... Okay, my code is wrong. I did something wrong. It gives you K. So that's pretty much what I had, right? Yeah, let's do this. So wait, we need to go back to test. First off, let's give it 0. Okay, that's good. So now we need to go back and test the one that I didn't. Oh, okay. So I actually got just like really lucky that. Yeah, so okay, good. Yeah, so I don't know what I did not understand. Okay, let's just okay, so I guess in general I would say that trans well, let's see. I guess one specifically 1,4 trans is almost always going to be both equatorial is going to be better. But and I would assume even for 1,3 but 1,2 trans you probably want axial. Or actually no, that was the punchline of this thing is that it actually ended up not being what you or was it that one? I forget which one it was. All right, let's just read the polycyclic stuff. Oh, that's cool. The final point we'll consider about cycloalkane stereochemistry is to see what happens when 2 or more cycloalkane rings are fused together along a common bond to construct a polycyclic molecule. Yeah, I was looking at decalin earlier. Decalin consists of 2 cyclohexane rings joined to share 2 carbon atoms, the bridgehead carbons C1 and C6, in a common bond. Decalin can exist in either of 2 isomeric forms, depending on whether the rings are transfused or cisfused. Oh, what? In cis-decalin, the hydrogen atoms at the bridgehead carbons are on the same side of the rings. What does that mean? Whoa, what the hell? Should we try to build decalin? Dude, we should definitely try to build decalin. Okay, so we need to build basically just we're gonna need 1, 2, 3, 4 of these. Let's see. I don't know I don't know what's gonna happen here. Yeah, this is a small one. What the hell? They didn't give me enough bonds. I deserve more bonds. No, these are the same length. Okay, I have some more. Okay, all right. Okay, I got it. The kit is actually pretty clutch. Only if it's just like because it's fun. It's pretty dope. I think that's the last. Oh, there's one more. Okay, so this is Decalin. Okay. The simplest. Well, not the simplest. Because you could probably have. Ooh, what is that called? If we go back and we draw like this, like this. What is that called? That's a weird molecule. Bicyclobutane? That's a dumb name. What's the IUPAC? Really? Bicyclo 1.1.0 butane? Bro, that's kind of insane of a name. That's a very cool molecule. All right, let's go back to the Decalin, though. So apparently what we can do instead, I believe, is we swap just this and this. Is that right? I don't know if that's right or not. Oh, because now these hydrogens are pointing right at each other, but I think that that's not supposed to be the case. Like if this one's sticking straight up. Actually, that does look pretty right. You probably can't see it. The lighting is all screwed up. But I think that does seem like cis-decalin. But the interesting thing is if you... They both look... Like if I really hold it like this, they both look axial up. It's weird. What are these things? Oh, that's for the freaking. That's dumb. For the what's it called? The buckyball. That's for the buckyball. Man, I forget what those buckyballs were. Those things, those magnets were so fun. Yeah. Bro, these ruled. These were so cool. Oh, getting them in the square form was the best. That was a blast. Oh, here we go with this bicyclo shit. I need a 3D model of this to play around with. Norbonane. I think I misspelled it. Norbornane. It's two pentane rings fused together. But its geometry is freaky because 1, 2, 3, 4, 5, 6. Oh, I get it. So if we 1, 2, 3, wait, I don't get it. Bicyclo 221 heptane structure. Like Declan and Norbornane is a bicycloalkane. So called because two rings would have to be broken. Oh, interesting. To generate an acyclic structure. It's the systematic name. Its systematic name reflects the fact that the molecule has 7 carbons, is bicyclic, and has 3 bridges. Oh, wow. That's weird. That's how they name it? That's weird. Based on the number of carbon atoms connecting the 2 bridgehead carbons. That's freaky. Norbornane has a conformationally locked boat cyclohexane ring, in which carbons 1 and 4 are joined by an additional CH2 group. All right, that's it for now. That was pretty interesting.